In today's discussion, we will be discussing about Gauss-Jordan method. The principle behind Gauss-Jordan method is to reduce or convert the augmented matrix into a diagonal or a unity matrix by row transformation. In our review of the matrices, when we say diagonal matrix, it means that diagonal elements of the matrix are all equal to 1, and the upper and the lower triangular elements are all 0. Gauss-Jordan method starts with Gaussian elimination. That is, first we need to convert or all the elements in the lower diagonal matrix into 0, and then continue with making all the diagonal elements in the upper diagonal into 0. So this method is used to eliminate the process of back substitution. For the sake of this discussion, we will be using our previous example. So that is, we have derived this equation using Gaussian elimination. Our first step, since we already have this matrix derived using Gaussian elimination, is to zero in all the elements here in column D. So we have to make all the elements above this diagonal element in D. We make all this into 0. And how do we do that? So here I have already prepared the matrix from our previous example, and note that in this example I have colored with lower diagonal matrix in order to isolate this one. That means we will not be doing anything with the values since we have already achieved our first goal, that is to make these elements here zeros. So for the rest of the solving, so we will not be touching these elements here. Instead, we will focus on the upper triangular elements. So our first step is to make or to zero in the elements above the diagonal element 1 in column D. So we will make these elements here above the diagonal element 1 into 0. And how do we do that? So we have here the formula. So we will be starting from the bottom to the top. So this element is in the third row, fourth column, and we need to make this one into 0. So the formula for R3 will be R3 minus E, or the element in row 3, column 4, times the element in row 4, which is 1, in order to make this into 0. So again, as I've said, we will not be touching these elements which are highlighted anymore. So we will be focusing only on the ones which are in white. So the new value of the element in row 3, column 4 will be using this formula, R3, that is 0.571429, minus the element in row 3, column 4, that is 0.571429, times the element in row 4, which is equal to 1. So that will give us 0. And we will also apply this to the succeeding element in the column of the same row. So R35, that is element in row 3, column 5, it is equal to the element in row 3, 3.714286, minus the element in row 3, column 4. So that is constant. Our E here is always constant. 0.571429 times the element in the row 4, which is equal to 4. So that gives us 6. So I will be putting these new values here to our new table. So we have here 0 and 6. So we have already zeroed these elements. So the next step is to make this element here 1 equal to 0. And how do we do that? So using the formula, the R2, because 1 is located in row 2, column 4, so the formula will be R2 minus the element in the second row, fourth column, times the element in the fourth row, in the row 4. So R23, because we still have the element here in the second row, third column, is equal to 2 minus the element in row 2, column 4. So that is 1 times the element in row 4, which is directly below 2, that is 0. So times 0 is 2. Then what is the value of the element here? That is R24 is equal to 1 minus 1 times 1, that is equal to 0. And the new value of R25, that is 5 minus constant, which is element in the second row, fourth column, 1 times the value of the row 4, which is negative 4, that will give you 9. So putting the values derived, so we have here 2, 0, and 9. And we will do the same with the values in row 1. So that will be R1 minus the element in the first row, fourth column, times R4. So R12, since we have here, we are to subject all the elements which are in white. So R12, so we are, that is 0.3333 minus the element in the first row, fourth column, element in the first row, fourth column, that is 1.333. So that is the constant here, times the value of row 4. So this is the value below, directly in row 4, that is 0. So that gives us 0.333. Next is R13, that is 0.667, minus the constant 1.333 times the value of R4 directly below C, row 4 is 0, that gives you 0.6667. Then the value here, 1.1333 minus 1.333 times the value of R4 directly below the D, times 1, that will give you 0, and R15 is equal to negative 1.333 times or minus this one, the constant value of E14 times the value of R4 directly below the element in row 5, that will give you equal to 4. So this is 0.333. This is 0.666. We have here 0, and this one is 4. So now we have achieved our first goal, that is to make all the elements above 1 as 0. So our next goal is to make all the elements above this 1 in the third row as 0. So we will make these two elements here into 0. So 0 in the elements above the diagonal element 1 in column C. So we have here the formula. So first, we need to make this element here 2 into 0. How do we do that? So the formula will be R2 minus the element in the second row, third column, multiplied by the element in third row. So again, we will not be touching this one. We will start with this one. The element in the second row, third column, R23 is equal to 2 minus 2 times element in R3, 1, that is equal to 2 minus 2, that is 0. Element here in 2, 4, that will be 0 minus constant 2 times the element below, which is 0, so the answer will be 0. And the element here, R25, is equal to row 2 value, which is equal to 9, minus constant 2, which is the element in 2, 3, times the value of row 3, or the value of the element directly below it in row 3, 6. That will give you negative 3. So applying that to here already the value 0, 6. Applying that to the table, so we have here 0, 0, and negative 3. So we have here 0, 0, and negative 3. So the next step is to make this element here into 0, because again our target is to make all the elements above 1 in column C into 0. And how do we make these elements here become 0? By applying this formula. The new value of R1 will be equal to R1 minus the element in R1 times the element in row 3, because again we are pivoting against this point 1 here. So that will be R12. So since we have to apply the equation on this row, so R12, that will give you 0.333 minus the constant E13, so that is 0.667, times the element below in row 3, so times 0, that will give you 0.333. In row 13, that is here, 0.6667 minus 0.6667 times 1, so that will give you 0. For row 14, that will be 0 minus 0.6667 times 0, so that will give you 0. And for the last row, that is equal to 4 to row 4 minus 0.6667 times 6. So 4 minus 0.6667 times 6, that is also equal to 4, so that will give you 0. So here we can apply the values that we have derived here to the table. This is 0, this is 0, and this is 0. Our last goal is to make the value of the elements above the diagonal element 1 in column B into 0. So lastly, this is the only element here which is not 0. So we have to make this element here 0 to satisfy the principle that we have to derive a unity matrix for our final answer, or to get the root of the equation, or to get the values of the unknowns for the equation. So in order to make this element into 0, we will apply the formula R1 is equal to R1 minus the element in row 1, column 2, times the value of R2. The pivoting point will be the one here, so that will be R2. So that will give us 0.3333 minus 0.3333 times 1, that will give you 0. For this element, that is 0 minus 0.333 times the element below here is 0, so that will still give you 0. The same here. And for the constant, that is 0 minus 0.333 times negative 3, so that will give you 1. So the values will be, so we already have values here, 0 and 6. We'll just copy the one here. 0, 0, minus 3. And we will have here 0, 0, 0, and the final value here is 1. So as you can see, we have attained our goal, that is to derive a unity matrix with the upper and the lower triangular elements as 0. One of the principles of Gauss-Jordan method is that it eliminates back substitution, because when you have derived the unity matrix, you can directly get the values of the unknowns. So in this case, the value of A will be equal to 1. The value of B is equal to negative 3 directly. C is equal to 6, and the value of D is equal to negative 4. So those are the derived values for our unknowns in the equations A, B, C, and D. So in our next topic, we will be discussing about Gauss-Seidel method.